Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Google TranslateGemma, Open Machine Translation Models based on Gemma 3. TranslateGemma is a family of open machine translation models built on top of Google's Gemma 3 foundation models. Instead of being general chatbots, these models are tuned specifically for translation at 3 different sizes: 4 billion, 12 billion, and 27 billion parameters. They cover over 55 language pairs in the WMT 24++ benchmark, plus many more additional languages, including low-resource ones. The goal is to provide strong, transparent models that the research and developer community can actually inspect, reuse, and build on. Machine translation underpins a lot of what we do online: reading news, accessing documentation, and communicating across borders. Large language models have pushed translation quality forward, but general chat models are not fully optimized for translation fidelity, consistency, and coverage. At the same time, many of the strongest MT systems are closed, which makes it hard for researchers to reproduce results or adapt them. TranslateGemma is meant to fill that gap: open, high-quality translation models that work across a wide range of languages and scripts. The TranslateGemma recipe has 2 main stages. First, the team starts from the multilingual Gemma 3 foundation models. They then run supervised fine-tuning on a large, carefully constructed mix of parallel data. After that, they apply reinforcement learning using several different reward models that directly target translation quality and naturalness. The end result is that, across 55 language pairs, TranslateGemma consistently outperforms the original Gemma 3 models. In many cases, a smaller TranslateGemma model matches or even beats a larger baseline, which is a big win for efficiency. A key ingredient is the training data. For synthetic data, the authors use Gemini 2.5 Flash to translate monolingual text drawn from the MATLAB 400 corpus, which covers hundreds of languages. For each language pair, they aim for up to 10,000 high-quality synthetic examples. To avoid relying only on synthetic data, they also bring in human-translated parallel corpora, especially for lower-resource languages. These come from the small and Gatitos datasets, which were designed to expand coverage to many underrepresented languages. The synthetic data is not just generated blindly. The authors first bucket monolingual sentences by length and sample a large pool of candidate sources. For each source, they generate 2 translations with Gemini 2.5 Flash, 1 greedy and 1 sampled. They score both with metric X24QE, a quality estimation metric, and keep sources where the sampled output clearly beats greedy decoding. Those are the cases where more aggressive sampling is likely to pay off. For those selected sources, they then generate 128 translation samples and again use metric XQE to pick the best. This process is applied both to single sentences and to longer text segments, so the model learns to handle both short and long-form translation. The supervised fine-tuning data spans hundreds of languages, not just the 55 language pairs in the WMT 24++ benchmark. The mixture includes both high-resource languages like German and Spanish, and many low-resource or underrepresented languages from small and Gatitos. The reinforcement learning phase uses a similar translation mix, though some human-only datasets are used only for supervised fine-tuning. This broad coverage helps the models generalize beyond the specific evaluation languages. One risk of heavy translation fine-tuning is that the model might forget how to do anything else. To avoid that, about 30% of the supervised fine-tuning mixture is generic instruction-following data from the original Gemma 3 training. This keeps the model from collapsing into a pure translation engine and helps preserve broader reasoning and instruction-following abilities, which can still be useful in many translation workflows. For supervised fine-tuning, the team starts from the released Gemma 3 checkpoints at 4, 12, and 27 billion parameters. They use the Cauldron SFT tooling with the Attafactor optimizer, a learning rate of 1e4, a batch size of 64, and run for 200,000 steps. All model parameters are updated, except the embeddings, which are frozen. Freezing embeddings turned out to help translation performance, especially for languages and scripts that are not heavily represented in the fine-tuning mix. After supervised fine-tuning, the authors apply reinforcement learning to push translation quality further. They treat the SFT model as the starting policy and optimize it using an ensemble of reward models. These rewards capture both overall translation quality and more fine-grained notions like naturalness. Importantly, they combine sequence-level rewards with token-level rewards, which improves credit assignment. The model can learn which specific spans of text caused a penalty or a reward, rather than only seeing a single score for the whole sentence. The reward ensemble is quite rich. Metric X 24XXLQE is a learned regression metric that predicts MQM-style quality scores without needing a reference translation. Gemma Auto MQM-QE is a span-level error model, fine-tuned from Gemma 3 on human MQM annotations, which can highlight specific error spans. CRIF is a simpler character n-gram overlap metric that uses synthetic references. The naturalness autorator is an LLM as a judge that flags spans that don't sound like they were written by a native speaker. Finally, a generalist reward model adapted from Gemma 3's post-training keeps the model aligned with broader reasoning and instruction-following behavior. In the RL algorithm, sequence-level rewards like metric X and churef are turned into a reward-to-go signal that is broadcast across all tokens in the output. On top of that, token-level advantages derived from span-level models like AutoMQM and the naturalness rater are added, so individual tokens or spans can be rewarded or penalized more precisely. The combined advantages are then batch normalized before updating the policy. This hybrid approach gives the model both a global sense of translation quality and a detailed view of where it went wrong. To evaluate text translation, the authors used the WMT24+ benchmark, which covers 55 language pairs. They report results with metric X24, where lower scores mean fewer MQM-style errors, and Comet22, a strong learned metric where higher scores are better. Across all three model sizes, TranslateGemma consistently outperforms the original Gemma 3 models on both metrics. In fact, the 12 billion parameter TranslateGemma model surpasses the 27 billion parameter Gemma 3 baseline, and the 4 billion TranslateGemma model reaches roughly the level of the 12 billion baseline. This shows a clear efficiency gain. Looking at the headline numbers, for the 27 billion parameter model, metric X drops from 4.04 to 3.09, and Comet rises from 83.1 to 84.4. For the 12 billion model, metric X goes from 4.86 down to 3.60, and Comet from 81.6 to 83.5. For the 4 billion model, metric X improves from 6.97 to 5.32, and Comet from 77.2 to 80.1. These are substantial relative gains. Importantly, Comet was not explicitly optimized in the RL phase, so the improvements generalized to metrics beyond those used as rewards. When you drill down to individual language pairs, the pattern holds. TranslateGemma improves metric X scores across all 55 evaluated directions. For example, English to German improves from 1.63 to 1.19. English to Spanish goes from 2.54 to 1.88. For lower resource languages, the gains are even more striking. English to Swahili improves from 5.92 to 4.45, and English to Icelandic from 8.31 to 5.69. This shows that the approach helps both high-resource and low-resource languages. TranslateGemma was trained with a consistent prompt template that explicitly states the source and target languages, including their language codes, and instructs the model to output only the translation. This same prompt is used during evaluation, and the authors recommend using it in real applications as well. The model repository includes tools to automatically wrap user text with this prompt, so you don't have to construct it manually. Gemma 3 can process images as well as text, and an important question is whether TranslateGemma preserves that capability. To test this, the authors use the Vistra benchmark, which focuses on translating text that appears inside natural images. They do not add any multimodal data during supervised fine-tuning or reinforcement learning. For evaluation, they simply feed the image to the model, along with a short prompt asking it to translate the text in the image, without any extra hints like bounding boxes or OCR output. On the Vistra benchmark, the team focuses on 264 images that each contain a single text instance according to the reference. For the 27 billion model, metric X improves from 2.03 to 1.58, and Comet from 76.1 to 77.7. The 12 billion model shows a metric X gain from 2.33 to 2.08, though Comet drops slightly. For the 4 billion model, metric X is almost unchanged, but Comet improves from 69.1 to 70.7. Overall, this suggests that the translation improvements largely carry over to image translation, especially for the largest model, even without any explicit multimodal fine-tuning. Automatic metrics are useful, but human evaluation is the gold standard. The authors run MQM evaluations, where professional translators mark error spans and severities on 10 language pairs. The source languages include English, Czech, and Japanese, and the texts come from literary works, news, and social media. For each language pair, they compare the 27 billion parameter Gemma 3 baseline with the 12 and 27 billion TranslateGemma models. They use the Anthea tool to collect annotations and follow a pseudo side-by-side setup where the same rater evaluates all systems for a given document. The MQM results mostly confirm the automatic metrics. TranslateGemma 27b generally has lower MQM scores than Gemma 3 27b, meaning fewer or less severe errors. The gains are especially notable for low-resource language pairs. For example, English to Marathi improves by about 1.6 MQM points, English to Swahili by about 1 point, and Czech to Ukrainian by around 1 point. There are a couple of exceptions. For German as a target, the models are roughly on par, and for Japanese to English, TranslateGemma actually does worse. A closer look shows that this regression is driven by more errors on named entities, even though other error categories improved. Beyond the WMT24++ set, the team generates synthetic data for many additional English-centric language pairs, including Armenian, Hawaiian, Western Frisian, Uyghur, Javanese, and others. The supervised fine-tuning mix also includes non-English pairs, such as Amharic to Arabic, Cantonese to Mandarin, Czech to German and Ukrainian, and Chinese to Swahili. This broad coverage is meant to make TranslateGemma useful, not just for a narrow set of benchmark languages, but for a much wider, more inclusive set of language communities. As you'd expect, larger models still deliver the best absolute translation quality. But TranslateGemma significantly narrows the gap between sizes. On WMT24++, the 12 billion TranslateGemma model actually outperforms the 27 billion Gemma 3 baseline, and the 4 billion TranslateGemma model comes close to the 12 billion baseline. This means you can get high-quality translation with much lower computational cost, which is important for deployment in resource-constrained settings. TranslateGemma is not perfect. There are clear regressions in some cases, such as Japanese to English, where named entity translation got worse, even as other aspects improved. The smallest 4 billion model shows only modest gains for image translation, likely due to limited capacity. The reinforcement learning setup depends heavily on learned metrics, and LLM as a judge reward models, which can themselves be biased or misaligned. And while the models retain multimodal abilities, there was no explicit multimodal fine-tuning in this work, so there may be room for further improvement there. To wrap up, TranslateGemma is a family of open, translation-focused models built on Gemma 3. The recipe combines supervised fine-tuning on a carefully curated mix of human and synthetic parallel data, with reinforcement learning guided by a diverse set of reward models. The result is consistent improvements across 55 language pairs on both Metric X and Comet, with smaller models often matching or surpassing larger baselines. At the same time, the models retain, and in some cases improve, their ability to translate text and images. These models are intended as strong, open foundations for future research and applications in machine translation.